All right, I feel really guilty here because I just told you about angular momentum and you're just wrapping your head around it. And I'm going to throw you a huge curveball. All right, actually I'm going to throw you a line drive. You know, a line drive is not a pitch. You'll see. I'm going to throw you, we're going to make the ball go straight. All right, that's what I'm trying to say. So here is the surprising thing. Masses moving in straight lines have angular momentum. I can hear people gasping even though we're not together. They still have angular momentum, but the value depends on where, oops, you put, this is getting very long, the axis of rotation. There we go. Okay, for real, here we go. So you have a mass. Let's say we have a mass sitting here, m. It's moving with a straight linear velocity, v. Just moving along, minding its own business along this axis right here. And you say, I believe this has angular momentum. I want to calculate the angular momentum about this point right here. You say, that is what I'm going to consider the axis of rotation. And I say, well, it's not rotating. So don't worry about it. We're going to call that the axis of rotation. Okay. Well, how do we calculate that? We actually need to use another formula for angular momentum. And that, in this case, would be L is R, where R is from the axis to the mass. So you think of the axis as the origin. And if we drew this as a vector, that's the R vector. But in this case, we're just using the magnitudes of the vectors. Okay? So R times P, and P is the object's momentum, so m times v. And again, though, we're just writing it as a scalar, as a magnitude, and times the sine of the angle between these two vectors. Okay, so the angle between these two, actually, got to pull this down here and say, there's theta. So what we're really doing is a cross product, if you're familiar with that, but we're not going to get into that level of vector detail here. And we're just going to write it as rp sine theta. So the value depends on where you put the axis of rotation. So you can see if I put it here or here or here, that's really going to change r and theta. So it really will affect the angular momentum. But what's interesting about this is that L is still constant. During the whole trajectory, as the mass moves along this straight line, if you only calculate the angular momentum with respect to this axis, you get the same thing. Think about it. If we had this get really far away, what two things would happen? One is the angle would approach 180 degrees, and r would get really long. Well, those two things cancel out, because sine of 180 is 0. So if this gets really long, this term goes to 0. But as they get really long, r gets really big. So those kind of cancel. And as you go this way, you get where it's 90 degrees. At 90 degrees, sine is 1. And that's the biggest sine gets. That's the smallest r gets. Then as you go this way, r gets big again, and sine goes to 0 again. And it all works out in a way where L remains constant, because we know angular momentum, even of something that's not even going in a circle, not even rotating, has to remain constant. It's a property of the universe. It's not a convenient description of something in our lab. Okay? So let's look at the special case of theta equals 90 degrees, and let's make something interesting happen. Let's look at theta equals 90 degrees. So theta equals 90 degrees is right when the mass passes the axis of rotation. And let's imagine that this mass on it has a very light little hook. Most of the mass is up here, but there's a light hook down here, and the hook is going to stick to the axis of rotation. Like the axis of rotation is like a pole sticking out. And this hook is going to capture it, and it's going to allow it to create a centripetal force to make the mass go in a circle. So we could kind of draw that like this. Here is the axis. Here is the mass. And we're right at the moment that the mass's hook captures the axis of rotation. Right? So let's think about what would the angular momentum be based on the linear motion, it would be what? So it would be L equals R. All right, so R is still just R. P is mv, that's fine. Theta is 90 degrees, so the sine of 90 is 1. So it would be R mv, according to this formula. But now, let's think about the fact that once this hooks on, what's it going to do? It's going to go in a circle of radius r. Okay? So we have circular motion of radius r. L is I omega if you have something that's rotating. So L is I. Well, let's see, what is I? For a point mass moving around in a circle, I is mr squared. All right. And what is omega? Omega is v over r, right? So we're talking about the angular velocity just from the speed as it goes around. So that's v over r. And you can see, sure enough, if you let this thing convert to circular motion, the r's cancel, and you get the same thing, mrv. So linear things do have angular momentum. The value depends on where you put the axis. Right? So if you put the axis right here, at this moment I'd get a different value, and it would be different around that axis. Even for something spinning, the angular momentum you would calculate depends on the axis you choose. And you say, well, how could that be? When we saw the disk, we saw it spin, and it was a certain I, and everything was fine. Well, you don't have to actually put your axis of rotation on the axis that's actually spinning. You could calculate those for different axes. It'd be crazy. Cause all kinds of trouble. It's nothing you should do, nothing you should worry about. But the point is actually the angular momentum is conserved, and it does depend on where you go, kind of like the moment of inertia depends on the axis you choose. Everything has angular momentum.